Hey that 5, so as usual we've got a starter, just one question, part A, B and C. So I want you to pause the video, complete the starter and then unpause it because I'm just about to go over the answers. So question 1A, name X and state the function of X. So X, it's completing the circuit, so it's the ion bridge. Okay, the ion bridge, and its function, as I just said, is to complete this circuit. Now how does it do that? It does that by allowing ions to pass from solution to solution. Okay, remember the electrons don't pass over the ion bridge, the electrons travel through the wires. Okay, now 1b, give a possibility for solution Y. So solution Y, we've got copper metal, so the solution has to be a copper solution, and you could have had copper sulfate, you could have had copper nitrate, copper chloride, phosphate, anything like that. Okay, the main thing is you've got a copper solution because we're dipping a metal into a solution of its own ions. Okay, so that's the answer to B. 1C, name a metal. Name metal Z that allows electrons to flow from copper to Z. So copper, the electrons are flowing from copper, so that tells us copper must be higher in the electrochemical series. So if we look at our electrochemical series, copper's here. Okay, so if copper's the higher metal, the other metal, metal Z, must be silver, mercury or gold. Okay, so our answer would be silver, mercury or gold. Okay, because remember the metal that's higher up, the electrons flow from the metal higher up to the metal that's lower down. Okay, right, so this is going to be quite a short lesson, but we'll get through it. So this is us finishing off metals. So this is lesson 6 and it's electrochemical cells part 2. Okay, so to get us started, we're going to look at the amount of voltage that's produced in electrochemical cells. So the amount of voltage an electrochemical cell produces depends on how far or close apart the metals are. Okay, so it's all to do with the positioning of the metals, whether they're far apart or whether they're close together. Now what you need to know, this pretty much sums up this entire section here, is the further the metals are from each other, the bigger the voltage. Okay, and you need to know that. Okay, so the further the metals are from each other, the bigger the voltage. The closer the metals are, the smaller the voltage. Make sure you know this. Very important, very important. So basically what we're saying here is the bigger the gap between the metals in the electrochemical series, the bigger the voltage. So if I give you a wee example, copper and magnesium, okay, if we set up copper and magnesium in an electrochemical cell, obviously a complex cell, a cell combining two half cells, it produces a voltage, let's just say, produces a voltage of 5.2 volts. Okay, so we did this experiment in class and that's what we got, 5.2 volts. If, however, if we change magnesium with calcium. So let's look at that. Okay, so we're starting off with copper and magnesium. So let's look at our data book, our electrochemical series. So we've got copper and magnesium. Okay, so the gap is pretty big. Yeah, so we're getting 5.2 volts. Now if we replace magnesium with calcium, hopefully you notice, yeah, we're going from magnesium to calcium, the gap is getting bigger. Okay, so magnesium, the gap's there. Okay, but if we change it to calcium, the gap's getting bigger. So because the gap's getting bigger, we should, in theory, get a higher voltage, and that's what happens. So if we change magnesium with calcium, the voltage goes up to 6.4 volts. Yeah, bigger the gap, bigger the voltage. If we change magnesium with iron, let's look at that. Yeah, if we change magnesium with iron, so let's go back to our electrochemical series. So we've got copper here and we've got magnesium there. So if we change magnesium with iron, hopefully you're seeing that the gap is getting smaller. Okay, so we're starting at magnesium, we're changing it to iron, and the gap is getting smaller. So because the gap's getting smaller, the voltage gets smaller. And that is what happens. So if we change magnesium with iron, the voltage goes down to 4.6 volts. Yeah, the numbers aren't important. All that's important is that the voltage is going down. Yeah, and that's because the gap is getting smaller. So make sure you know that. The bigger the gap, the bigger the voltage. The smaller the gap between the metals, the smaller the voltage. Now the last thing we're going to do is all about making a cell with just one metal. With one metal. Now, I always told you in previous lessons that we needed two different metals to create an electrochemical cell, and that is true. Okay, you can't create an electrochemical cell with tin and tin or magnesium and magnesium. It has to be two different cells. However, we can do it with one metal and a non-metal, but in solution. You'll see what I mean by that. Okay, so we'll highlight this, making a cell with one metal, and this will hopefully, if you've been looking at your electrochemical series, you'll maybe notice, oh, hang on a minute, there's some non-metal equations there. What's happening? But we'll go through that. We'll go through that. Right, so I'm going to draw very quickly. I'm going to draw an electrochemical setup. I'll draw a complex cell. You as well. I'm just going to do it freehand. If you want to do it with a ruler, by all means. Like that. Yeah, so we've got our solutions in. In order for us to complete the circuit, what do we need to add? We need to add an ion bridge. Okay, so we'll label that ion bridge. And let's just call this metal zinc. Okay, so that means this beaker is zinc sulfate. Okay, zinc sulfate solution, or again, it could be zinc nitrate, it could be zinc chloride, but what's important is that they're both zinc. Okay, now this time, instead of having this as a metal, we're going to make this a carbon rod. Okay, and in order for this to work, it has to be graphite, and hopefully you realise why it's graphite, because graphite is the only non-metal that can conduct electricity, so that's why we're using graphite. Now in here we're putting iodine solution. Okay, so we are only using one metal and we're using a non-metal solution. Okay, and we're using a graphite rod because one, it conducts electricity, and two, it's not reactive, so it's not going to react with the iodine or anything like that. Okay, now this does in fact produce a voltage. Okay, now what we need to do is we can set up a redox equation. In order to do that, we need to use the data book. Okay, so use data book to get equations. Now, if we look at this, our metal is zinc and our non-metal is iodine. So zinc is here. Okay, now you might have noticed looking through this, so you've got the metals on the left, but on the right side, sometimes you've got a non-metal like bromine, chlorine. Yeah, there's other ones, you've got hydrogen peroxide as well, but yeah, so chlorine, bromine, and the one we're after is iodine. Okay, so hopefully you're noticing zinc is higher than the iodine. Yeah, now bringing everything that we've learned together, so zinc is higher than iodine, so goes through oxidation. Okay, because remember what we said, the one that's higher up is the one that goes through oxidation, yeah, and then the one that's lower down, in this case iodine, goes through reduction. Now when we're writing our, remember we need to, if we want to write our overall redox, we write oxidation, we write the reduction equation, and then we combine them to form the overall redox. We've been doing that, we've had a lot of good practice at that. Okay, we've had a lot of good practice at that. Now, zinc is the one that's going through oxidation. So remember what we do to the oxidation one, we flip the equation, so the product becomes the reactant and the reactants become the products. Okay, so this becomes zinc solid goes to zinc 2 plus aqueous plus 2 electrons. Yeah, now remember, get your arrows directly underneath each other, makes this so much easier. Yeah, now reduction, we'll look at iodine, I2 solid plus 2 electrons goes to 2I minus aqueous. We write the reduction just as it is because it's gaining electrons. Remember, oil rig, so that is I2 solid plus 2 electrons goes to 2I minus aqueous. Okay, now the good thing about this, the electrons, they're already balanced, so we don't even need to multiply one equation or whatever, they just cancel out. And then finally, the ones that are to the left of the arrows, we write to the left, and then the ones that are to the right of the two arrows, we write to the right. Yeah, so Zn solid plus I2 solid goes to Zn2 plus aqueous plus 2I minus aqueous. And that's it, that's how we would write the redox for a metal and a non-metal solution. And that's it. Okay, so this is metals finished. The biggest thing to take from this lesson is that essentially the bigger the gap, yeah, so the further apart the metals are, the bigger the voltage, the closer they are, the smaller the voltage. Okay, so if we look at nickel and lead, quite a small gap between them. If we substitute lead with copper, we get a bigger gap, so we're going to get a bigger voltage. Yeah, if we substituted nickel with tin, we're getting a smaller voltage, a smaller gap, so that means we're going to get a smaller voltage. Okay, and just be aware that we can also create electricity using a metal and a non-metal solution if we dip a carbon rod graphite in the solution. Okay, so we'll leave it there. I'm going to put up some questions for us to do, and it will be a summary of every sort of lesson we've done on metals, and then next week we'll move on to nuclear chemistry. Okay, so thank you.